As a matter of fact, gamma rays are our enemy. We can't have neutrons without having gamma rays, and the gamma rays transfer energy to the detector system, mostly through Compton scattering in the walls of the detector, the anode wire, and less commonly in the gas fill itself. Most source materials, emit more than 10 times as many gamma rays as neutrons. So from the beginning, you have to worry about how to discriminate against gamma ray interactions. There are 4 basic strategies in helping to discriminate neutrons from gamma rays. One is to simply add gamma ray shielding material, such as lead, around the detector to reduce the number of gamma rays hitting the detector. Because the thermal neutron to gamma signal ratio is generally much better than the fast neutron to gamma signal ratio. Another strategy, as we talked above, is to moderate the neutrons so they interact more readily and we get more neutron signal. For some detectors, the interaction products deposit much more energy than do gamma rays. For example, helium-3 or with boron, the charged particle formed are very densely ionizing radiations compared to the electrons that are produced by gamma rays. And for a variety of applications, this difference is enough to allow the use of these neutron detectors in moderate gamma fields. Finally, the same effect can be used to discriminate against gammas. Because the collection speed for the induced charge for neutron products and for gamma rays may be very different, we can use pulse height discrimination techniques to separate neutron events from gamma events. This table shows the interaction probabilities typical for various types of detectors and typical wall thicknesses. For thermal neutron detectors, a helium-3 detector with a 1-inch diameter tube pressurized to 4 atmospheres has about a 77% chance of detecting a thermal neutron traversing the detector. A 1 MeV gamma ray only has 0.01% of interacting with the chance of interacting with the helium-3 gas in the detector, and only about a 0.05% chance in an argon-filled detector. The reason that the interaction rate for gammas is higher in argon, even though the pressure went from 4 atmospheres to 2 atmospheres, is that the increased Z of argon more than offsets the loss of pressure. For a BF3 tube with a 2-inch diameter tube loaded with 2/3 of an atmosphere with BF3, there's about a 30% chance of the neutron interacting with the BF3 and only about a 0.06% chance of a gamma ray interacting with the boron trifluoride. Thermal neutrons hardly react at all with aluminum tube alone, but unfortunately there's about a 1.4% chance that a 1 MeV gamma will interact with this 0.5 millimeter thick wall and produce an electron that will introduce noise into the detector. Now looking at fast detectors, if you use a helium recoil detector with a 2-inch diameter tube loaded to 18 atmospheres, goodness gracious, a 1 MeV neutron has about a 1% chance of interacting as it traverses the detector. The bad news is that gamma rays have about a 0.1% chance of interacting with the gas in the detector, so you have about a 10-to-1 signal-to-noise ratio within the gas itself. With the aluminum tube, the interaction probability for a 1 MeV neutron is close to 0, but unfortunately it's about 1.4% reaction probability by the gamma ray, which again introduces a spurious signal into the sensitive volume of the tube. For scintillators, there's about a 78% chance that a 1 MeV neutron will interact in a 2-inch diameter tube, and there's about a 20% 26% chance that gamma rays will also interact. So you only have about a 3-to-1 signal-to-noise ratio. Let's look in more detail at the ratio of the amount of charge put into typical detectors from neutrons versus the amount of charge put into typical detectors by the interaction of gamma rays in the gas or in the walls of the detector. For a helium-3 detector with a 1-inch diameter tube pressurized to 4 atmospheres, the range or alphas of protons is only a couple of centimeters, and the range of electrons is much greater than the tube dimensions usually. The average neutron reaction energy deposited in the tube is on the order of 500 keV. The energy deposited from the electrons created by the gamma rays is on the order of 4 keV. So there's a signal-to-noise ratio of about 125. For helium-3 with argon added, the counting gas is better, but the signal-to-noise ratio drops to 30-to-1 because the argon interacts more readily with the gamma rays. With the BF3 tube, 2 inches in diameter, pressurized to 2/3 of an atmosphere, it's about a 90-to-1 signal-to-noise ratio. For fast detectors, our game is harder, and we only have about a 20-to-1 signal-to-noise ratio, and with scintillators, we only have about a 2.5-to-1 signal-to-noise ratio.